So in this video we'll look at the last part of the 2D shapes in area and volume. Then we had this diagram from the start of question 21 here in 21A, and we worked out the diagonal. We were given the diameter of the circle was 50, so we had this diagonal being 50, and we worked out x to be 35, which was the side of the square, and that was rounded off from 35.35. What percentage of the circle is covered by the square? Well, we have to just work out a percentage here, simple enough. So we have pi r squared for the circle. I'll use 3.14 by 25 squared. It's going to give 1962.5. The area of the square is 35 by 35, which is 1225. And we're asked what percentage of the circle is covered by the square. So it's 1225. That's the part of the circle, and the total of the circle is 1962.5. So the bit that's covered by the square, if we take that and multiply it by 100, it's giving me 62.42%. To one decimal place, we're asked 62.42, 62.4%. Now, what have we got here? We've got this triangle. The drawing in part A, this one, represents a circular piece of wood. The square is to be cut out, and 3 of the remaining parts, okay, so this part here, 1, 2, 3 of these guys are used here in this design here. So what can we say about these guys along here? Well, we can say that the straight part of them is 35. So that side of the triangle, it's going to be, they're all going to be 35 for the triangle. So we're asked find to the nearest centimeter the height of the triangle. Okay, well we can use Pythagoras there. We have the half of the bottom. So let's do that. And then hence find the area of the triangle. So we have this is 35. So this has to be 17.5. So x is equal to the square root of 35 squared minus 17.5 to be squared, which is 30.31. X is equal to 30, nearest centimeter again as 30. Hence find the area. So half the base is 35 by the height, which is 30. So 1535 is 350 and 175, which is 525, and it's in centimeters squared. So question 22, what are we dealing with here? The diagram below shows the chain of a bicycle passing over cogged wheels. Okay, so here's our chain, and we have A, B, and C. So we have 3 circles. Let's just take them out. So we're given a lot of information. Radius of 5, radius of 2, radius of 21. Okay, so a lot of times they give these diagrams, and the question is actually a lot easier than it seems. So if you look at part A here, the circumference of wheel C. Well, circumference is 2 pi r, which is 2 by 3.14 by the radius of C, which is 21. And that gives 131.88. Don't think it asks us around here, does it? No, okay. The bicycle travels 990. So that means that 1 turn of C will be the circumference of the wheel. So if this is touching the ground here, it goes around, and when it gets back to here, the bike has traveled that distance. Obviously, the distance, that's how they use the speedometers on bikes, and you put your attachment on, and every time it comes around, it adds the circumference of the wheel onto your GPS or whatever you're using. So 131.88. Now that's in centimeters, 1.3188 meters. I see this guy up here is in meters. So 990 divided by 1.3188 will tell you how many times the wheel has turned. That's given me 750.68. So they haven't asked us to round, so I'm not going to. and then the number of times that wheel A turns. It does say take pi is 22/7 here, so we would round this off to 132 and 750 for these two, but just to be a bit more accurate, I've used 3.14. The number of times that wheel A turns, well, here's wheel A and wheel B. So what do we know about those? A, the radius is 5, and for B, the radius is 2. So what's the difference between these? So the circumference of 2 pi r. So for A, we get 2 by pi by 5, which is 10 pi for the circumference. And for B, 2 pi by 2 is 4 pi. So B moves 4 pi in one circumference and A moves 10 pi. And the number of times that A turns, well, we figured out that C turned 750. So B turns the same, it tells us up here, B turns the same. So if B turns 750, A has to turn less than that, and it's by a factor of 4 by 2.5 is 10. It's a factor of 2.5 in the difference. And 750 divided by 625, 300 and 300 and 150 is 300. So A will turn 300 times. What's next? This diagram, not to scale, represents a shot put zone in an athletic stadium. So it's a sector of a circle, quarter of a disc. So we have a right angle in the middle there. You can see tiny little right angle in there, and the radius is 100. So we have 100 meters here. Big radius for a shot put. Radius 100, center C. Calculate the area. So it's pi r squared is the area. Pi r squared divided by 4 will give us the sector. So 3.14 by 100 squared divided by 4. It's asking me for 2 decimal places, so use pi in your calculator and you'll get the 2 decimal places. I'm just going to round off here. It's 7850 is what it's giving me. So get your 2 decimals, use the pi button on the calculator because the 0.14 here is getting moved up by the hundreds. So the shot put zone consists of a throwing zone and a landing zone. The throwing zone shaded yellow, we can see here this yellow throwing zone, is a disc with center C and radius 1 meter. Calculate the area of the throwing zone. Well, if the radius is 1, the area of the throwing zone is a circle, pi r squared. So pi by 1 squared is just 3.142 or whatever. So 3.14 meters squared. It's a bit of a silly question. The landing zone is the unshaded area. So what are they asking us? Calculate the total area of the landing zone. So we just want to take away this quarter of a circle here from the whole thing, which is 7850. Could that really be the question? So we have 7850 meters squared. We want to take away a quarter of this guy. So we're going to take away 3.14 over 4. It's just a quarter, isn't it? Not 3/4, just a quarter of it, yeah. But my rounding, that's going to give 7849, obviously. 7849.22 if we round it off to 2 decimals. Now I know the answers in the book will be slightly different than this, but I've rounded off the beginning here. And part B is this diagram here. I think this was a past junior cert question. There's 2 circles at the end here. 28 from here to here is 28. So we also have a 7 in at the end here and a 7 in at the end here. So 2 pulley wheels of equal size connected by a drive belt. The radius is 7 of the wheels and the distance between the center is 28. Calculate the length of the belt and give your answer to the nearest whole number. So if we imagine that the belt has these 2 semicircles at the end of it, we could say that this whole circular end and this one would add up to 1 full circle, and then we're left with 28 here and 28 here. So we have 56, 2 by 28, plus just 2 pi r, 2 by pi by 7, 56 plus 14 pi, and 14 by 3.14 is 43.96, 56 plus 43.96 is 99.96 to the nearest whole number, 100 centimeters for the length of this drive belt, and the end of 2D shapes within area and volume, and we're going on to look at rectangular solids and prisms next. So master 2D before moving on to 3D.